All right. So we're going to continue to talk about Chapter 11 here. Chapter 11 is again talking about alkyl halides, but specifically these reactions of alkyl halides that are in competition with one another. Substitution reactions where you have an alkyl halide and that halogen is considered a leaving group. And so what happens is that leaving group is substituted with that nucleophile to create a new functional group, right? So you're swapping functional groups in your substitution reactions. And that's what we spent a lot of time last class talking about. It turns out depending on the alkyl halide, specifically depending on the classification of that alkyl halide, primary, secondary, or tertiary, they go through different substitution mechanisms. Some of which, both of these steps, the bond breaking and formation happen at the same time. In other ones, the bond breaks first, so you get this carbocation intermediate, and then in a second step, the new bond forms, right? So we discussed those various mechanisms. Elimination reactions, we kind of just introduced in this very broad way here, talking about how in an elimination reaction, again, your halogen's going to leave. It's playing the role of a leaving group, but so is a neighboring hydrogen, all right? And so what's going to be involved here is a base that's going to need to remove that neighboring hydrogen, and you're always going to get the same functional group at the end of an elimination reaction, an alkene. Okay, so this would be removing a halogen and a neighboring hydrogen to create a carbon-carbon double bond, an alkene. Okay, so again, last time we did this like deep dive into the substitution part. Today we're going to go into the elimination part. And then on next week, on next Monday, we'll sort of talk about the competition between the two and how can you tell which one's which, right? And again, there's a bit of a competition because we see certain molecules are both good nucleophiles and good bases, right? So for example, hydroxide, we know to be a good base. Hydroxide is also a really good nucleophile. It's a nice electron-rich species. And so with some alkyl halides, your hydroxide ion will favor the substitution reaction. In other ones, it'll favor the elimination reaction. So how do we tell? All right, so that's what we'll sort of save for last here. Again, today we're going to focus only on these elimination reactions. All right, so elimination reactions. So first of all, let's just note here, sort of just to review what I was saying before, let's take a generic alkyl halide. Okay, and again, now we call this reagent is going to be playing the role of a base here. That's the important bit. And again, at the end, we get an alkene. All right, but let's put in our implicit hydrogens because I just want to make an important point here. All right, on the substrate side, both of these terminal carbons have 3 hydrogens. On the product side, that sp3 hybridized carbon still has 3 hydrogens. All right, how many are up in this middle carbon here? Just 1. So I don't lose that one. But on this N carbon here, since this is sp2 hybridized, I have only 2 hydrogens. All right, so in terms of our bonds that are broken here, not only are we going to break that leaving group bond, we also have to get rid of one of those hydrogens. All right, and again, that's why a base is an important player in these reactions. And then on the flip side, what's being formed is that carbon-carbon double bond. All right, so We will talk about the mechanism of these reactions, but before we sort of get into that, there's one other thing we want to talk about. This was a relatively simple alkyl halide. There's only one possible elimination product here. But what if we take just one larger carbon, right? One more carbon on here. Okay. Again, we'll just say we're doing an elimination reaction. There are actually two possible elimination products here. I want everybody to take a second and see if they can't draw me the two possible elimination products. Actually, there's actually three if we do stereochemistry, so let's make it easier. Boom. Now there's only two. All right, so an important requirement for these substitution reactions is our leaving group is going to leave along with the hydrogen from a neighboring carbon. So the only two places that I could possibly have a double bond forming is between carbons 1 and 2 or between carbons 2 and 3. All right, so those are my two possible alkenes that I could get here. Right, one if the double bond forms on one side, and the other if the double bond forms on the other side. Okay, two distinct alkene products here. The 3-methyl-1-butene or 3-methyl-2-butene. All right, so two distinct products that we could get. Importantly, though, something that I really want to stress is always for these elimination reactions, this carbon that is bonded to that halogen is going to be involved in that double bond, right? That carbon right there has to be one of the carbons with that double bond. All right, so then we get these two possible products here. It turns out that for this reaction, this would be the major product, and this one would be the minor product. And there's a decent amount of the minor product in these reactions, like 30 to, I don't know, 20 to 30%, something like that. Okay, so it's not something that we can discard altogether. But why is this product the major product and this one the minor product? We talked a lot about alkenes, but there was one particular topic that I was saving for this chapter here, and that is the idea of alkene stability. Okay, alkene stability depends on the degree of substitution. Of those sp2 hybridized carbons. So what do I mean by that? Let's take a look at some alkenes, same molecular formula here. All right, we're going to do a bunch of alkenes that share the formula C5H10. Okay, so the first one to come to mind, kind of the easiest one here, the 1-pentene. This is what we would call a mono substituted alkene. Because if we look at these sp2 hybridized carbons, there's only one carbon neighbor. If we move that double bond over, okay, this would be a di-substituted alkene, because again, if we look at these sp2 hybridized carbons, there are 2 carbon neighbors. All right, and then we can sort of rearrange. Another constitutional isomer here would be, if I picked up that methyl group and moved it, okay, and so this would be, if I look at my sp2 hybridized carbons, they have a total of 1, 2, 3 carbon neighbors. So this would be what we would call a tri-substituted alkene. Okay, and all right, this isn't going to have the same formula, but just to throw it out there, you can have up to 4 or a tetrasubstituted alkene, right? Something that would look like this. Or you have 4 carbon neighbors, but this is a different C6H12. All right, so if we compare these constitutional isomers with that same formula here, it turns out that alkene stability depends on the degree of substitution. A tri-substituted alkene, the more highly substituted, the better. So this is the most stable alkene, and this is the least stable alkene, my mono-substituted. Okay, right, so then why did we say that our previous, and we looked, the reaction that we looked at, one product was the major product, one product was the minor product? Well, my major product is a tri-substituted alkene, and my minor product is just a mono-substituted alkene, right? So the more stable alkene will be your major product. If we wanted to illustrate this with a free energy diagram, all right, and just speaking of free energy diagrams, super random aside, but don't let me forget today that I have your exams. I just completely forgot on Monday. All right, but yes, we'll see your exams. All right, so I'm going to do my major product in blue. Okay, and I'm going to do my minor product in red. My reactants are the exact same, so I'm starting out at that same energy level. There's really no difference in the transition state energy The difference is simply that my product is less stable. My minor product is less stable, so it has a higher free energy. And truthfully, this is probably a little bit exaggerated. Again, you do get a good bit of minor product, so they're pretty close together. It's nothing too crazy. All right, but the reaction will favor the more stable alkene, which is again going to be the more substituted alkene. All right, so what do you say? More substituted is our major product. All right, let's take a look at another one. Again, we're just going to say that this is an elimination reaction. Okay, this one actually has 3 different products that you could draw here. See if you can't get me the 3 different products for this reaction. So again, my double bond has to form with the carbon at the base of the halogen, so it can form either over here or over here. So let's draw those. Oops. So here are 2 of them. What's my third one? Let's go ahead and name these. What's the name of this one right here? 1 butene. And what about this one? 2 butene. You're not getting full credit for that one. What's missing from this name? Which is what? Which is, so for this one here, what would this isomer be? So this would be E2-butene. So then what's my third product? Z2-butene. Okay? We have to watch out for our stereochemistry here, because although we draw these structures as these zigzaggy lines, they are, of course, are not frozen like that in solution. They are constantly rotating about all of their single bonds, and so you will get some of your molecules that are in both of your stereochemistry conformations. Okay, so based on what we discussed 2 seconds ago, what's going to be the minor product here? Based on alkene stability. The 1-butene, right? So based on alkene stability, so let's just say minor product, because of alkene stability. So then let's take these two and look at them next to each other. These are both have the same degree of substitution. So in terms of that, there's no difference between these two. Both of these are di-substituted alkenes. All right? There is still one that is more stable than the other one, though. Which one do we think? E or Z? Let's take a poll here. Who thinks E is more stable? And who thinks Z is more stable? No, yeah, so the E, right? Big groups like to be pointed on opposite sides. And to be clear, you will get a mixture of all three of these, but your major product will have large groups on opposite sides. So we can just lump this into the minor product bin as well. Now, like among minor products, which one's the minorist? I don't know. Don't worry about it, all right? We don't have to go crazy with that. Bottom line is we should be able to spy what the most stable alkene is in the bunch. All right, so let's just practice this real quick. I'm going to put down another alkyl halide. Okay, and I want you to draw me my elimination products. All right, so let me show you a strategy for how we're going to make sure we get all of our products here. All right. Again, I know it has to, my double bond has to contain that carbon right there, the one at the base of my halogen. All right, so it's either going to form on this side over here or on this side over here. All right, so let's just take, copy and paste our alkyl halide. I'm going to get rid of that halogen, form a bond on one side, a double bond on one side. Going to do the same thing, but now I'm going to form the double bond in the opposite direction. Okay, but now I got to ask myself, for each of these structures, is there a stereo isomer? Because right now I kind of did it lazily where I just took my zigzaggy just as it was drawn above and I just kind of made a double bond there, right? But that's not necessarily all possible structures, so I have to look. Is there going to be a stereo isomer for this molecule right here? Does this have E or Z stereochemistry? Yes, remember, how do we spy that? It wouldn't if these two groups were identical, but they're not. They're different on all four, or on both of those carbons. So then everybody take a second if you haven't already. This currently, as drawn, this is the E isomer. Okay, give me the Z isomer, the one that's really weird to draw because it's not our normal zigzaggy shape that we're used to, right? It's like a little unnatural. Okay, so to be clear, to get my other stereoisomer, I'm going to either need to swap these two groups right here, or I would get the same structure if I swapped these two groups right here. Either one of you would give you the Z isomer. So I'm going to swap that ethyl group and that methyl group. So now that larger group is pointed down. So there's my Z stereoisomer. All right, everybody take a second. Actually, let's just look. What about this one? Does this one have a stereoisomer? Are these two groups the same? No. Are these two groups the same? No. So then it definitely has a stereoisomer. So everybody take a second. Again, this would be the E. Take a second and draw me the Z stereoisomer. All right, so I'm going to swap this methyl group and this hydrogen. So I'm going to redraw this structure, but now with that methyl group pointing down. Boom. So we would get a mixture of 4 alkenes out of this. And I want you to take a second and hunt through these 4 and tell me which one is going to be the major product of this reaction. All right, so on the left-hand side, these are both tri-substituted. And on the right-hand side, these are both di-substituted. So what's better, di or tri? Right? The higher degree of substitution, the more stable the alkene. So I know that's going to be one of these two here. All right, so then which one of these two is going to be my major product, the E or the Z stereoisomer? Do I want these two ethyl groups on opposite sides or on the same side of that double bond? Opposite. So this will be my major product, and then I'll get a mixture of the other 3 as my minor products. Okay, And again, I'm not worried about you ranking minor products. I'm worried about you being able to draw all possible products and being able to identify which one is going to be the major product amongst that bunch. Okay, and again, sort of how do we make sure we get all possible products? Let's say step 1. We draw in our double bond on our structure as it's given above. All right, I just said, okay, I'm going to remove that chlorine, put a double bond over here, draw another structure where I put it over there. And then 2, I need to ask myself, after I've drawn those, is there a stereoisomer? Right? Am I going to be able to draw another stereoisomer for those alkenes? If so, I got to include those as well. All right, and then lastly, what is the major product? It's going to be the most substituted alkene. Large groups on opposite sides. Which honestly 99.9% of the time is the E stereoisomer. There are just some weird exceptions to that I don't want to make that grandiose statement and have it be some random example where it's not true, all right? But generally speaking, the E stereoisomer is going to be the one that has the largest groups on opposite sides. All right, so then one more y'all are going to do from scratch. We'll use our our best leaving group halogen iodide. So I'm going to copy my alkyl halide, and I'm going to put in my double bond with my structure just as it's drawn in the problem, right? So get rid of that halogen, put a double bond on the left, do another one where I get rid of the halogen, put a double bond on the right. All right, at this step, you want to probably stop and make sure you didn't just draw the same structure twice. In this case, they are distinct, 2-hexene and 3-hexene. So then I'm going to ask myself, Is there a stereoisomer? Do either of these have stereoisomers? Yeah, both of these are the E conformation, so I would have to draw the Z conformation. So now I want these two groups pointed on the same side. All right, so then let's go through this first one, mono, di, tri, tetra substituted. What is it? So this one's di, which means that it's stereoisomer is di. What about my other product? Also di. So in this case, if I asked you for the major product, it would be both. We have a tie here. These are both the E stereoisomer, where big groups are on opposite sides, and they have the same degree of substitution. So I'll get these four products out of my elimination reaction. Two of these will be what we would classify as our major product. All right, we'd get like 40, 40, 10, 10, or something like that. I don't know, I just totally made up those numbers. But both of them would be produced in about equal quantities, right? Because they're both di substituted and both have the correct stereochemistry in terms of having those large groups on opposite sides of that double bond. All right, so now let's talk about our mechanisms for elimination. All right, so again, we're just going to take an example, alkyl halide here, and we're going to combine that with some generic base to produce an alkene. All right. Now, we sort of already did this at the beginning. We went through and we said, all right, what bonds need to be broken? We need to break both our leaving group bond, but also we got to get rid of this hydrogen too, right? That's the only way we're going to be able to form a double bond. And then in terms of what bonds are being formed, that new carbon-carbon pi bond, right? All right, so keeping this in mind here, we have one mechanism which we call an E2 mechanism, which is analogous to our SN2 mechanisms, all right, where our bonds are broken. And bonds formed, all in one step. Say it again? It's E2 because we're talking about elimination, not substitution. All right, so see if you can't put in our electron pushing arrows. Given what we said about the bonds that we want broken and the bonds that we want formed, let's put in those electron pushing arrows, doing it all in one shot here, right? All in one step. All right, and to make it a little more clear, I will tell you that you also get a bromide ion and a hydrogen attached to your base at the end. All right, so if we're being good and listing all of our products here, we would have both a bromide ion and a hydrogen on that base by the end of this. All right, so we're going to have our base do what bases do and remove that hydrogen. So it's going to attack that hydrogen. Okay. We're going to break this bond. I'm going to draw that in last year. Let me just make a point here, because we're also going to break this bond to form our bromide ion. All right. So I need to break this bond right here as well. We identified that. But I also need to form this bond. And again, that happens all in one shot. So where did that pair of electrons that becomes my pi bond come from? That was that pair of electrons that was in that carbon-hydrogen bond. So my double bond, we get a bond breaking and bond formation arrow all in one shot here. All right, we got everything listed. We got bond formation. Let me use a different color. We have bond breaking. All right, but then we have this arrow here, which represents a break and formation all in one. All right, because again, that pair of electrons that was in that carbon-hydrogen bond, that is that same pair of electrons that makes up my new pi bond in my product. Okay, and again, we call this an E2 mechanism, analogous to an SN2 mechanism. It happens all in one step, just a one-step reaction here, one-step mechanism rather. So where does the 2 come from? Similar to before, there are these 2 molecules. They're alkyl halide and the base involved in that first step. All right. And we got 3 different arrows here, right? We have our bond formation arrow, our new hydrogen base bond. We have our bond breaking arrow, releasing that leaving group, that bromide ion. And then we have a breaking and formation arrow, one that happens in both shots, where we break that carbon-hydrogen bond but form that new carbon-carbon pi bond. All this happens in one step. Again, we call that E2. Cool. All right, so now let's learn E's 1 through 5. All right, no, I'm kidding. There's only one more. All right, and analogous to before, we also have an E1 mechanism, which is going to go through a carbocation intermediate. And just like before, the name of the game in terms of bonds breaking and bonds formation is the same. I'm still trying to break these bonds. Still trying to break the same bonds and form the same new bonds, all right? So given what we discussed before about SN1, See if you can't complete my mechanism here to form our alkene. Alright, so step one, just like before, our leaving group leaves. So boom, gonna kick off that leaving group, leaving me with that carbocation intermediate. Alright, what's the base gonna do? What do bases do? Yeah, I take hydrogens, right? So I don't have any explicitly drawn hydrogens here because of course we leave them implicit. So I'm gonna have to draw one in for my mechanism. And I'm going to steal this proton, okay? Now, if you try to, truthfully, this then happens in one step, these two arrows here. And let me just show you real quick. If you try to break it into two steps, you would have an illegal intermediate here where you have a carbocation located right next to a carbanion. This thing will absolutely never form. You're never going to have a carbon with a negative charge next to a carbon with a positive charge. Instead, like we saw before, that pair of electrons that was in that carbon-hydrogen bond is going to form that new pi bond. So again, we have a bond-breaking, bond formation arrow here. All right, but again, this happens in two steps here. First, for our E1 mechanism, just like we saw before, our E1 mechanism, just like our SN1 mechanism, is two steps. First, we have that leaving group leave, forming our carbocation intermediate. And then in the next step, step 2, is that base removes the hydrogen and we get our new pi bond. So then if it's two steps, why is it E1? Again, kind of backwards here. That's because only one molecule, that alkyl halide, is in that first step. All right, so that rate limiting first step, the only molecule involved is that alkyl halide.
So I have a question for the S23s in the bromine. Where is the other molecule for bromine? Because they look like very similar. So what is the two molecules that remove that makes this an S2?
So this is an elimination, so it's an E2 because they happen at the same time. This isn't a bromine, it is a base.
Yeah.
And so it's removing that hydrogen.
So for the base of this one and the iodine. Oh wait, no, it's not. No, it's not.
Yeah, so like again, well, I think maybe the confusion is that we're lazy in organic chemistry. So if I was really good, The other thing that I would include at the end here is my inorganic products, my hydrogen attached to my base, and my iodide ion. All right, those are both formed as well. We just get lazy and we only show what happens to our organic molecule. All right, so much like our substitution reactions, we have these different mechanisms for our elimination reactions. Okay, an E2 mechanism where everything happens in one step. We get our bonds broken, this bond breaking and formation, and then lastly that leaving group leaving all in one shot. Okay, so E2 is in one step, E1 is in two steps, where we get that carbocation intermediate, because first that leaving group gets popped off, and then in the next step our hydrogen gets removed and our new pi bond is formed. All right, so if you noticed last time when we introduced these mechanisms, I had already said at the beginning, oh, primary and secondary are always this mechanism, and tertiary is always this mechanism. It's a little bit more complicated for the elimination, and we'll talk about that when we get to the competition step on Monday. For now, I'm just going to tell you E1 or E2 going forward here. Okay? There's one other huge pain in the butt difference between these mechanisms. All right? And in particular, the pain in the butt is with these E2 mechanisms. Okay, so E2 mechanisms, and everyone's least favorite word, stereospecificity. Okay, so I'm going to take an alkyl halide. Let me actually turn it around. All right, so here is an alkyl halide. I'll go ahead and make this. Boom. Now, everybody's going to do what I know you've been just so pained to not have done in so long, and that is to give me the Newman projection looking down this bond here. We're not done with the semester yet, y'all. You can't forget it all. All right, give me the Newman projection. These aren't bad. You just have to remember that they actually exist. right? So remember, the whole shtick about the Newman projection is here's my eyeball, and I'm looking down this particular bond. So this front carbon here is represented by the intersection at the beginning, but then this back carbon, which is sitting along that same bond, we represent with the circle. Right? So I'm trying to draw the bonds that are coming off of the front and the back carbon in my Newman projection. What's pointed up on that front carbon, that blue carbon, is that methyl group. Since that bromine is on a wedged bond, it's pointed out of the board. Does that go on the left or the right of my Newman projection?
Right.
On the right. Right? It's pointed out at me. So if I took this and turned it this way, the bromine is pointed out. So it's pointed to the left. So then So then that means what is sticking out over here on the left-hand side of that blue carbon? Hydrogen.
Wait, did you just say
Wait.
sticking to the left and then you put it
Okay.
to the right?
Hold on. My bad. I don't know my left from right.
We know this.
Okay. The bromine is going to be sticking out on the right-hand side of the Newman projection because it's on a wedged bond pointing out of the board. So yes, I put it in the right place and just don't know my left from right very well. Whatever side this is, that's the side it goes on. So then what's on the left? A hydrogen, okay? So then if I look on my back carbon, what's sticking down is this whole ethyl group here, CH2, CH3. And then if I'm going to put that methyl group in, which one do I put it on? On the right-hand side. All right, cool. Okay, so why is this important? We're going to do this elimination reaction. And I'm going to tell you that this is an E2 mechanism here. In order to have an E2 mechanism, remember, this is when all our bonds get broken and formed, all in one shot, right? The hydrogen and the bromine, really whatever halogen it is, has to be anti from one another. And remember, what does this word anti mean? They have to be pointed on opposite sides. So in this molecule here, my bromine and my hydrogen, these are of the neighboring carbon, right? Not on the same carbon, but of the neighboring carbon, the hydrogen that's going to get removed, are anti from one another. So I'm only going to get one stereospecific product from this, from elimination of that carbon. Okay, so let's just draw it out again because it's got a little messy. All right, I'm going to draw in that implicit hydrogen explicitly here so we can show that they're pointed in opposite directions. So again, if I have this E2 mechanism, my hydrogen and my bromine are on opposite sides, so this is going to lead to a stereospecific product. Boom. Okay, where my methyl group specifically is pointed up. I'm not going to get my other stereoisomer here because then those hydrogens and those halogens wouldn't be anti from one another. So I'm only going to get this E isomer here. Okay, the other thing I want to note, because this was one of the mistake that I saw a lot on one particular problem on the exam, no dashes or wedges about a double bond. All right, let me just show you real quick what would be wrong if you gave it to me, what I don't want to see. This right here, you cannot represent as a wedge. That would be incorrect. Remember, alkenes are flat. All of these bonds are in the same plane. So you have to represent them with those straight lines. So no dashes or wedges about a double bond. All right, so let's just do another one real quick. Let's make sure. If we just, real quick, this would be my major. I would still have that minor product where it formed on the opposite side. I just don't have to worry about that stereochemistry-wise because there's two hydrogens. And this one you would have to leave as a wedge because it's not about the double bond. All right, so let's just do another one for practice. Okay, and I want the E2 product, and for the sake of simplicity, we're going to say when our double bond forms right here. Alright, so if I'm looking at my double bond forming here, my implicit hydrogen on this carbon is pointed into the back. So are those halogens and hydrogens on opposite sides? One's on a dash, one's on a wedge, right? So one's pointed into the board, one's pointed out. So they are indeed anti from one another. So in order to draw my alkene product, I'm just going to put in my double bond and flatten out that wedge. So here's my double bond. And again, I'm not going to draw a wedge here because that would be wrong. I have to just draw a straight line. Boom. Okay, and again, my H and I are anti. They're on opposite sides. All right, so then obviously the next step is like, what the heck do we do if they're not already anti? Right, so let's do a similar example. But now instead of this methyl group being on a wedge, on a dashed bond, if I put in my hydrogen, now my H and I are not anti. So what am I going to do to figure out what my product is? We need to rotate to put the hydrogen in the back. All right, and so we've talked about rotating bonds before. Okay, my hydrogen's sticking out. I need it in the back, so I'm going to move that to where that methyl group is. That means my methyl group needs to become that straight line bond. I'm going to make this really ugly with a bunch of markings. So let me clarify. Okay, so if we're going to rotate, we need to swap all three groups. I want my hydrogen to be where that methyl group is. That means I need to move my methyl group where that ethyl group is, and the ethyl group will then be on that wedged bond. So now on the wedge is the ethyl group. On the dash is the hydrogen. And the straight line is just my methyl group, right? So you have to swap all three of them. You can't just switch two of them. You got to rotate. So you got to move all three of those groups, like you're turning a steering wheel. Okay, so now my hydrogen and my iodide are on opposite sides. So now we can draw in our E2 product. Right, so we have our methyl group, but now that ethyl group is what's sticking up. Okay, so notice that if I start with two different stereoisomer alkyl halides, I get these two different stereoisomer alkenes as my products. Okay, so this is obviously worst case scenario here, right? So, when do we have to worry about E2 stereochem? Right? What was it about this particular reactant that made it such a pain in the butt? Because both the carbon containing the halogen and the carbon containing the hydrogen are chiral centers. Okay, so when do we have to worry about E2 stereochemistry? When both the C halogen and CH are stereocenters. If they aren't both stereocenters, you don't have to worry about it. You're going to get your mixture products just like you would with E1 mechanisms, but if both of them are stereocenters, as is the case here, then you do have to worry about your stereospecificity of these E2 elimination products. Cool. All right, so let's pack everything up so we can pass out exams. All right, as always, you can ask me any questions you want. You just can't take any notes or pictures, and I'm going to collect them at the end.